This is part 2 of exercise. I forgot what exercise. 5H. Exercise 5H. We just found the inverse matrix using the calculator. That was with a 2x2 matrix. We want to now manually find this. Now there is a lot of new terminology that's involved with this. There are a lot of steps that might seem a bit random. There are many proofs, as to why this works. We're not going to delve into that. We're going to just look at the process, okay? So, if you're given a matrix A that has 4 elements in the formation of a 2x2 order, A, B, C, and D, these numbers can represent any numbers, negative, positive, decimal, etc. There is a calculation which is called the determinant. Okay? And the determinant is a specific calculation that we need to obtain first in order to get the inverse of a matrix. To work out the determinant, whatever your A, B, C, and D matrix is, it has to be within that order. So A, top left, B, top right, bottom left for C, bottom right for D. You get A and D, multiply them. You get B and C, multiply them. And you find the difference between the two. Okay, A times D, subtract B times C. Be very, very careful with your negatives. Okay, they do play an important role. Now, just for a note, for a matrix to have an inverse, its determinant, so this calculation that you work out from a 2x2 matrix, must be non-zero. Okay, if the determinant is equal to 0, then an inverse does not exist. And A, the matrix A, is what's considered a singular matrix. So when you hear the word singular matrix or the term singular matrix, it means that the determinant, when you calculate it, is 0. There will be instances where this does happen. Okay. So now that you've worked out the determinant, or you've seen how to work out the determinant, to calculate the inverse, all you need to do is obtain 1 over A times D minus B times C. A times D minus B times C is the determinant. Okay, you put this under 1, or you put it as a fraction 1 over whatever that is. Then this will become a scalar, and you multiply it with D minus B minus C and A. All this is doing is taking D, whatever D is within the original matrix, and you're putting it in this position where A is meant to be. B still stays the same, it just turns into a negative. If it's already a negative, it turns into a positive. Same thing with C, same position, and then A is in the bottom right. So what we're doing is kind of like this weird flip around. B and C turn into a negative, and D and A swap around. So you do that, and you're multiplying it by 1 over the determinant. Okay. When you actually apply this, remember the scalar. The scalar is just whatever this is multiplied by each element. So the next line is showing what happens when 1 is multiplied, or 1 over the determinant of A is multiplied by D. This is just showing that it turns to D over the determinant of A. If this is multiplied with negative B, same thing. Negative B over the determinant A. Okay, same thing with negative C and A. Now, you will only complete this here, and so these little 2 stars, if your answer gives whole numbers. if the answer gives whole numbers. You will also complete it if it gives finite decimals or appropriate fractions. Alright, let's look at an example. So, example 1. Find the determinant for both of the following matrices. We've got matrix A and matrix B. So, matrix A, to get the determinant, get position A and D, so 6 and 2, multiply. Get position B and C, multiply, and find the difference. 6 times 2, 12. 3 times 4, 6. 6 is your answer for the determinant. For B, same thing. 4, 8, 3, 6. Multiply 4 and 6. Multiply 3 and 8. Find the difference. In this case, the determinant is 0, as 24 minus 24 is 0. C, are the matrices singular? And explain. So, a matrix will become singular, or it's determined, not become singular, but is determined as singular if the determinant is 0. So, C, this isn't singular, as the determinant is non-zero, because we got 6 before. But the other matrix, matrix B, is singular, because the determinant is equal to 0. And the last question, I will go back down. If possible, calculate the inverse. We can't calculate the inverse of matrix B because the determinant is 0, but we can determine the inverse of matrix A. This is going to be 1 over 6 because the determinant is 6, so it's 1 over 6 multiplied or used as a scalar to A and D get swapped around. So 2 becomes this element here, and 6 is here. And these elements have a negative in front. So negative 3 and negative 2. That right here, we keep it as our inverse. If you were to get this inverse and multiply it with the normal matrix, you will get the identity matrix with a lead of diagonals of 1s. And that concludes that lesson of identity and inverse matrices. Go ahead and check out the questions for exercise 5H on your log sheet. And I'll see you soon.